Today we are going to derive the flexural stress and shear stress due to the shear and bending moment here. Before we do the derivation, what we need to know some terminologies here. We know after we were trying to bend the beam, our beam is going to be deformed like that. And then you can see on the top is under the compression. And the bottom is under the tension. So the length of the fiber is going to change. However, there is a length that's not going to change. The length of this layer remains the original length. And this is going to be called neutral axis, or sometimes called neutral surface here. So now the curve of the beam is going to be called the deflection curve. So now what we need to know is another thing called pure bending. So which means there is only head bending moment. There's no shear stress. So how could we find this pure bending kind of structure? We can do the cantilever under just a moment. Or what we can do is try to have a simply supported beam here, and we try to apply the load at 1/3 of the load, 1/3 of the length. So you can see if we were trying to plot the moment diagram for this structure here, it will look like that. Would be PA. And why? Because for the shear, it will look like, okay, we had a P going up and down here. And then we had another P here. So you can see the area here is P times the length A, and then that's why. So you can see in the middle of this region here, we had a moment is not going to be 0, but your shear is going to be 0. So this is going to be called pure bending here. So let's talk about the Euler Bernoulli beam, and we are going to derive the equation from there. So those are all the assumptions that we need to make before we do the derivation. So in this assumption here, you need to watch that the vertical normal strain is going to be ignored when we try to derive the formula here. So now you can see what we are going to do is, okay, so let's try to set up a beam, a coordinate system. So try to think about this is a cantilever under the bending moment here. So we just try to take a part of the beam out. So maybe this is X from the support, and the length is going to be called delta X here. And on this here, let's try to find a point on the neutral axis. So let's say A and B. And what we are going to do is try to draw the vertical line. And then on this line, let's try to find out another 2 points here. It's called P and Q. And let's try to link them together. Remember, they are going to be perpendicular, and the distance from A to the P, that's going to be called Y. Okay, so now we apply the moment. It will curve your structure, right? So which means after the deformation, we might have something kind of looks like that. And then remember, AB is on the neutral axis. So now it might go to different location like A star and B star here. And then what we can see is after the deformation, so the whole thing is kind of like being curved around a center. So it might have a curvature kind of like this. I didn't draw that passing the B point, but you understand this. Okay, so which means after the deformation, so the P and Q might go to a different location, and it will be marked as P star and Q star here. And we are going to call this angle here as delta theta star. Okay, so now, one more thing. From here to the neutral axis, that's the radius. Let's use the rho here. So this is a different rho definition from the torque. But anyways, let's try to keep moving here. So now what we can see is the length of PQ actually changed. So which means what we need to do is try to study what is the normal strain in the PQ. So which means we are going to, if we approach the Q to P point here, and then how we are going to calculate the normal strain in PQ, we are going to use the final length minus the original. And then let's divide it by the original. That's by the definition of the normal strain. And then, which means our length, differential length, approach to 0. We had, if we say this is going to be delta x, so we had a delta x star minus delta x over the original length, delta x here. So which means this is delta x, this is delta x star here. Okay, so now AB is on the neutral axis. So which means the length after the deformation here will be equal. So that's why when I mark the length from A star to B star, I didn't put a star on it. I still use delta x here. Okay, so now let's take a look at here. A star, B star, it's an arc length. We should be able to use the arc length to find out what is exactly the delta x is. So which means it's going to be the radius times the angle that we had. It's a small angle here. So similarly, we will be able to calculate PQ star, the arc length, which is delta x star here. So you can see there's no deformation, remember, in the y direction, which means this length doesn't change. It will still going to be the y. So which means we are, when we try to calculate delta x star here, we are going to use the radius. Now it will be rho minus the y, and then we times the angle here. So which means what we can do is try to go back to the epsilon x here. So we already know we have to put everything into this equation. And then, which means we already find out everything here. Rho minus y delta angle and divided by the rho times the angle here. And every term had the angle, we can cross them out. And then we all had a rho here, so which means if we combine everything, eventually we had y over rho. And don't forget about this negative sign here. Okay, so which means that's the strain displacement equation we just derived. However, we are not going to memorize this equation yet. This is just the intermediate kind of equation here. Okay, so now let's keep moving to the next page. You can see this is the summary of the strain displacement. So when we try to derive the normal strain in the axial loading direction, it will ignore the deformation. However, the transverse strains actually can be obtained by using the Poisson's ratio here. But it will be very small, right? It can be ignored. Okay, so now let's try to derive the flexural stress equation that we are going to use in the future. So basically, under the moment, we are going to have equation my over I to calculate the flexural stress. So now let's see how we are going to have this equation being derived. So let's take a look at this picture. So you can see on the whole cross-sectional area here, if we apply the moment at the bottom, we are going to have a tension, but on the top, it will be compression here. So now our task is try to calculate the moment around z-axis here. So now let's see how could we calculate moment. Based on the moment definition, it will be the force times the distance. So that's why we had df times the y here. However, when you try to use your right-hand rule, when you curl, following the arrow, the compression, and above the z-axis here, you can see there is a negative sign here. So don't forget about it. And then take a look at here, we had a df here. In order to find out what is the df, the force on the differential area here, that's actually going to be the stress times the area. So that's why you can see we try to rewrite df in the stress times the area form. And then after this, we are going to think about Hooke's law, because the stress is equals to the Young's modulus times the normal strain. And remember, we just derived the normal strain here. It's negative y over rho. So let's put it in here. Eventually, we are going to have the differential moment form equals to the E over rho times y squared dA. In order to find out the total moment, we have to do the integral for the whole area. After this, we should be able to find out the moment under what is the total moment. It will be EI over rho. So now let's take a look at here if we combine everything. So this is the equation we just derived. And remember that from the Hooke's law, the normal stress equals to the E times the epsilon. And remember, the epsilon is negative y over rho we derived at the first part. So if we combine all the equation together, this is the flexural stress formula for the Euler Bernoulli beam. I had a different video to talk about something the sign convention for this. You can watch for the different video. But anyways, sigma, the flexural stress, it's actually the normal stress under the bending moment. If you want to calculate, it will be my over I. M is the internal moment, and y is the distance from the neutral axis, and I is moment of inertia.